So this video is going to talk about something called heat of formation, which is, again, part of our discussion on thermochemistry. And heat of formation, you might have seen in a previous problem, is called enthalpy of formation. Okay, so it's going to be an H. F is going to be a lowercase letter, and then you have this little degree sign. I'll explain what that is. So when we look at the overall reaction, we're always looking at products minus reactants. So what you have in this equation is the number of moles. So little n is number of moles. Okay. And then what is the heat of formation of the products versus heat of the formation of the reactant. So this is enthalpy of formation. So it is the formation of 1 mole of a compound from its elements. Okay, that is what the definition is. So if you go to Appendix C in the back of your book, you will see a table of all different substances and their corresponding delta H's. Well, delta H for the formation of an compound is going to be dependent upon, again, what condition you are at. So the little degree sign that you see on the top here is because we are at standard conditions of 1 atmosphere, 25 degrees Celsius. This is different than something called STP, which is standard temperature and pressure, which is actually 0 degrees Celsius. So standard conditions are always at 25 degrees Celsius, 1 atmosphere, because then the substance would change depending upon your state of matter. So with this idea of heat of formation, all elements on that table, when you look at it, are going to have a heat of formation of 0 because the elements exist in our system, meaning they exist on our planet, and that's how they are in terms of what state of matter. But if I take those elements and make a compound, the heat of formation is going to be determined based on what the substance happens to be. So the first example I want to show you here is the formation of water. Okay. So all elements are going to have a heat of formation of 0. That also includes diatomic. So you will see hydrogen and oxygen both have a heat of formation of 0. If you were to go to Appendix C and you looked up water in the gas form, you would see this number, negative 241.8 kilojoules per mole. That means when water forms, it releases energy. Okay, so this is exothermic. So that is what we call a favored thing that we talked about before previously. So if I want to know the delta H of the whole reaction, I'm going to take the products, which is negative 241.8, and I am going to multiply that by 2. So I'm going to multiply that by 2 because according to the heat of reaction, I need to multiply it by the number of moles. And since I have 2 moles of water molecules in this equation, I'm going to multiply it by 2. I then subtract the reactants. Well, both of these are 0, so I subtract from 0. So my overall delta H of this particular reaction is going to be negative 483.6 kilojoules. Okay. So that means when water forms, I'm going to get that much energy out. And again, being negative, that's going to make it exothermic. So again, I'm going to give you numbers for these types of calculations, and then you're going to be asked to calculate certain things. So I'm going to combine this also with the delta E that we were talking about before as well to kind of make it a little bit more interesting. So if I give you the delta H of formation of HF, O2 is of course going to be 0 because it is an element, water in the gas state, and then OF2 in the gas state. And again, if you look at Appendix C, different substances might have a different delta H because of the state of matter, gas, liquid, or solid. So the first thing I want you to find is the delta H reaction of the whole thing, okay? And then I want you to talk about or calculate or figure out what would the delta E and the delta H reaction happen to be. in relationship, sorry, reaction, that makes no sense. Is delta E greater than delta H? Is it less than, or is it equal to? So I'm going to pause the video and then come back. So your delta H is going to be, again, products minus reactants. So your products here are just HF. You have to multiply that by 2. Oxygen is not a part of this. And then you have the OF2 and then the H2O. So you should get negative 318.4 kilojoules. Okay. So then the more interesting question is, of course, the delta E versus delta H. So what is your delta N here? Okay, I have 3 moles of gas on the product side, and I have 2 moles of gas on the reactant side. So I have a 1 associated there. So if I have my delta H, which again, if my delta E is equal to delta H minus nRT, okay, my delta H is negative 318.4, okay, and I know my delta N is positive 1, so whatever the R and the T happen to be. So then what I want to explore is, well, what's that delta E going to be? Well, because this is negative and an exothermic, and this is going to add to it, my delta E magnitude-wise is going to be greater than my delta H, okay? So again, we're not going to do the calculation. Instead, I want you to explore the delta E versus delta H relationship. Okay, all right, so then the other problem to kind of show you this is this one. Okay, so this one, I am giving you the overall delta H of this whole reaction. I'm giving you the heat of formation of the B2O3, and I'm giving you the delta H of the liquid water. And I'm asking you to find the missing component, okay? And then I also want you to explore the delta E and the delta H relationship. So again, I'm going to pause the video and then you're going to. Okay, so the first part of the problem is you had to find the missing B2H6 in this equation because you had everything else. So here is my heat of reaction. Here is my B2O3. I have 3 times the water molecule. And again, oxygen on the reactant side is an element, so it is 0. So then all I have is my missing reactant, which is X. So that comes out to be about 31.4 kilojoules per mole, okay? Because again, this is the relationship of when B2H6 is formed from its elements of B and H, it's going to be an endothermic process, so it is a positive number. So then the second part of the question was, what's the relationship between delta E and delta H? So again, you are looking at states of matter. So I have no gases on the the product side, so that's why it's 0. And then over here I have 4 moles. So I'm going to take products minus reactants, so I get a negative delta N, negative delta N. So if I go back to my equation, delta E is equal to delta H minus nRT. Well, my delta H happens to be negative. It is exothermic. It was given in the problem. And I have a minus delta N. Well, that's a 4, a negative 4. So that becomes essentially a positive. So whatever I multiply that by, the R and the T, the temperature and the constant, the negative 2153 magnitude-wise is going to go down, okay, because of the fact that I'm adding a positive quantity to it. So my relationship between delta E and delta H is delta E is going to be less than delta H magnitude. Okay? And I know some of you are going to struggle with this, so just always think magnitude. If you want to put that next to the problem, that would be helpful as well.